material properties of the hammer also play a vital role in its performance. The ability of the hammerhead to absorb and dissipate energy during impact is determined by its material composition. High-carbon steel, for instance, is commonly used for hammerheads due to its superior hardness and resistance to deformation. When a hammer strikes an object, the material's hardness ensures that the hammer retains its shape while transferring maximum energy to the target. However, the material must also possess sufficient toughness to withstand the repeated stress of impacts without fracturing. This balance between hardness and toughness is a key consideration in the engineering of effective hammers, as it directly affects their durability and performance in demanding applications. Furthermore, the dynamics of impact introduce the concept of energy transfer efficiency. When a hammer strikes an object, not all the kinetic energy is transferred effectively. Some energy is lost as heat and sound. This energy loss can be minimized through careful design choices, such as optimizing the shape and surface texture of the hammerhead. For example, a flat striking surface distributes force more evenly, reducing the risk of material damage and maximizing the transfer of energy to the target. This engineering consideration is crucial in applications like metalworking, where precise shaping and minimal waste are essential. The engineering and physics behind the hammer are deeply intertwined with principles of momentum, kinetic energy, leverage, material science, and energy transfer. By manipulating the mass, velocity, and design of the hammer, engineers can create tools that are not only efficient but also effective for a wide range of applications. As we continue to innovate in tool design, the fundamental principles governing the behavior of hammers remain constant, reminding us that even the simplest tools are a product of intricate engineering and physics. Through an understanding of these principles, we can appreciate the craftsmanship behind hammers and the role they play in shaping our world. The choice of materials for the head and handle of a hammer is based on an intricate understanding of material properties, which includes factors such as hardness, toughness, and energy absorption. For the hammerhead, steel is often the material of choice due to its ability to endure high-impact forces without deforming. This property of steel is achieved through heat treatment processes like tempering, which involves heating the steel to a specific temperature and then cooling it rapidly. This process alters the internal structure of the steel, balancing its hardness and toughness. If the hammerhead were too hard without adequate toughness, it could become brittle and shatter under a strong impact. Conversely, if it were too tough without sufficient hardness, it could deform easily, losing its effectiveness. The precise control of these material properties through metallurgical processes ensures that the hammerhead can deliver powerful blows repeatedly while maintaining its integrity. For the handle, materials such as hickory and ash are traditionally preferred due to their excellent mechanical properties. Hickory, in particular, is known for its high strength-to-weight ratio, making it both strong and relatively light. This property is crucial because a handle must be robust enough to withstand the forces exerted during hammering while being light enough to allow the user to swing it effectively. Additionally, hickory has a natural ability to absorb shocks, which reduces the vibrations transmitted to the user's hand and arm. This shock absorption is a critical ergonomic consideration, as it minimizes user fatigue and the risk of repetitive strain injuries. The fibrous structure of hickory allows it to flex slightly under impact, dissipating energy that would otherwise be transmitted to the user. This combination of strength, lightness, and shock absorption makes hickory an ideal material for hammer handles. Modern innovations have introduced materials like fiberglass and composite handles, which further enhance the ergonomic properties of hammers. Fiberglass handles, for instance, are engineered to offer superior shock absorption and durability compared to traditional wood. The internal structure of fiberglass consists of fine glass fibers embedded in a resin matrix, which provides excellent tensile strength and resilience. This composition allows fiberglass handles to absorb and dissipate impact energy effectively, reducing the transmission of vibrations. Moreover, fiberglass is resistant to environmental factors such as moisture and temperature changes, which can degrade wooden handles over time. This makes fiberglass handles more durable and longer lasting in various working conditions. Composite materials, which often combine multiple substances to enhance specific properties, are also increasingly used in hammer handles. These materials can be engineered to optimize the balance, strength, and shock absorption characteristics of the handle. For example, some composite handles incorporate carbon fibers, which are known for their exceptional strength and stiffness, into a polymer matrix. This results in a handle that is both lightweight and extremely durable. The ability to tailor the properties of composite materials through careful selection and combination of constituents allows manufacturers to create hammer handles that provide maximum performance and comfort for the user. The physics of the hammering process also involves the concept of energy transfer and dissipation. When a hammer strikes an object, kinetic energy from the hammer is transferred to the object, exerting a force over a short duration. The efficiency of this energy transfer is influenced by the mass and velocity of the hammerhead, as well as the material properties of both the hammer and the object being struck. A well-designed hammer maximizes the transfer of energy to the object, achieving the desired effect with minimal loss of energy. This efficiency is crucial in applications where precision and power are necessary, such as driving nails or shaping metal. The design of the hammer handle plays a significant role in the overall dynamics of hammering. A handle that is too rigid may transmit excessive vibrations to the user, causing discomfort and reducing control. Conversely, a handle that is too flexible may absorb too much energy, diminishing the effectiveness of the hammer blow. The ideal handle strikes a balance between these extremes, providing sufficient rigidity to transmit force effectively while absorbing enough energy to minimize user fatigue. This balance is achieved through careful selection of materials and design features such as ergonomic grips and anti-vibration technologies. The engineering and physics behind the choice of materials for hammer heads and handles are deeply interconnected, involving a delicate balance of mechanical properties to achieve optimal performance. From the metallurgical processes that enhance the hardness and toughness of steel heads to the selection of hickory and modern composites for their strength, flexibility, and shock absorption, every aspect of the hammer's design is meticulously engineered. This ensures that the tool can deliver powerful, precise blows while minimizing user fatigue and maximizing durability. The next time you wield a hammer, consider the sophisticated interplay of material science and physics that makes this seemingly simple tool so effective. Ergonomic design is critical to the effectiveness and safety of a hammer, a concept that extends far beyond mere comfort. The handle must be shaped to fit comfortably in the user's hand, considering the diverse range of hand sizes and gripping styles. This requires a detailed understanding of human anatomy and biomechanics. Engineers employ anthropometric data, which includes measurements of hand dimensions and strength, to create handles that accommodate a wide spectrum of users. The contour of the handle is meticulously designed to follow the natural curve of the human hand, reducing the effort required to maintain a secure grip and thereby minimizing muscle fatigue. Additionally, the balance of the hammer achieved by precisely positioning the head and tailoring the handle's length and weight distribution ensures that the tool feels natural and intuitive to wield, further enhancing its usability and reducing the risk of strain injuries. Modern hammers often feature contoured grips that integrate advanced materials designed to enhance comfort and performance. These materials are selected based on their ability to provide a firm grip, even in conditions where the user's hands might be sweaty or oily. For instance, thermoplastic elastomers, TPE, are commonly used due to their superior grip characteristics and their ability to absorb sweat. The surface texture of the grip is also engineered to increase friction, using patterns that can vary from simple ridges to complex, biomimetic designs inspired by the gripping abilities of animal appendages. This attention to detail ensures that the hammer remains secure in the user's hand, reducing the likelihood of accidental slips that could result in injury or damage to the workpiece. Anti-vibration technologies are a crucial advancement in modern hammer design, addressing the issue of strain and discomfort from prolonged use. When a hammer strikes an object, the impact generates vibrations that travel through the handle to the user's hand and arm. These vibrations can lead to conditions such as hand-arm vibration syndrome, HAVS. If not properly mitigated, engineers employ various strategies to reduce these vibrations. One approach is the use of multi-material handles that combine rigid cores with flexible, vibration-damping outer layers. The core provides the necessary structural integrity, while the outer layers, often made of materials like rubber or foam, absorb and dissipate the vibrational energy. This principle is akin to the damping systems used in skyscrapers to absorb seismic energy, illustrating the crossover of engineering concepts between different fields. Further innovation in anti-vibration technology includes the incorporation of dynamic dampers, which are devices that move in opposition to the vibrational forces, thereby cancelling them out. These dampers are often tuned to the specific frequencies generated by the hammer's impact, effectively neutralizing the vibrations that are most likely to cause discomfort. This technology is derived from the principles used in precision machinery and automotive engineering, where controlling vibrations is essential to performance and longevity. By adapting these principles to handheld tools, engineers have significantly improved the usability and safety of hammers, allowing for longer periods of use without detrimental effects on the user's health. In addition to these advanced technologies, the ergonomic design of hammers also involves optimizing the length and shape of the handle to enhance leverage and control. A well-designed handle allows the user to apply force more efficiently, maximizing the impact energy delivered by the hammerhead. This requires a deep understanding of the mechanics of lever systems. The handle acts as a first-class lever, where the fulcrum is the point where the hand grips the handle. The effort is applied by the user's muscles, and the load is the hammerhead. By optimizing the length of the handle and the position of the grip, engineers can increase the mechanical advantage, enabling the user to deliver more powerful blows with less effort. This principle is similar to that used in the design of high-performance sporting equipment, where maximizing power output and control is crucial. Moreover, the design process must consider the dynamic forces at play during the hammer swing. The motion involves complex interactions between the user's muscles, the hammer, and the object being struck. Computational models and simulations are often used to analyze these interactions, allowing engineers to refine the design for optimal performance. These models take into account factors such as the angular velocity of the swing, the distribution of mass in the hammer, and the impact forces, providing insights that guide the design of both the handle and the head. By integrating these engineering and physics principles, modern hammers achieve a level of precision and efficiency that enhances both their effectiveness and the safety of their users. The ergonomic design of hammers is a multifaceted challenge that incorporates elements of human anatomy, material science, mechanical engineering, and physics. By leveraging advanced materials, anti-vibration technologies, and sophisticated design principles, engineers have created hammers that are not only more comfortable and safer to use but also more effective in their intended tasks. This continuous innovation ensures that the humble hammer remains an essential and efficient tool in a wide range of applications, embodying the perfect blend of simplicity and technological sophistication. Understanding the physics behind hammering involves concepts such as force, energy, and impact dynamics. When you swing a hammer, you convert muscular energy into kinetic energy. Upon striking an object, this kinetic energy is transferred to the object, exerting a force that drives nails, shapes metal, or breaks materials. The efficiency of this energy transfer is influenced by the design and material properties of the hammer and the object being struck. The conversion of muscular energy into kinetic energy is a fascinating process that showcases the principles of biomechanics and mechanical advantage. As a user swings a hammer, muscles in the arm and shoulder contract, creating rotational motion around the shoulder joint. This motion is further amplified by the length of the hammer handle, acting as a lever to increase the speed and force of the hammerhead. The longer the handle, the greater the mechanical advantage, allowing a relatively small input force to produce a significantly larger output force. This principle is evident in sledgehammers, which, with their long handles, can deliver substantial blows with less effort compared to shorter-handled hammers. Upon impact, the hammerhead's kinetic energy is transferred to the target object. The efficiency of this transfer depends on several factors, including the mass and velocity of the hammerhead, the hardness and shape of the hammer face, and the properties of the material being struck. A heavier hammerhead, moving at the same speed as a lighter one, will impart more energy to the target due to its greater momentum. However, simply increasing the mass is not always practical, as it also requires more effort from the user to swing the hammer. Therefore, there is an optimal balance between mass and ease of use that engineers must consider when designing hammers. The shape and hardness of the hammer face also play crucial roles in energy transfer and impact dynamics. A flat, hard face is ideal for delivering concentrated force to a small area, making it effective for driving nails or chiseling metal. The hardness of the hammer face ensures that it can withstand repeated impacts without deforming, while the smooth surface reduces the chance of slipping off the target. On the other hand, a hammer with a textured or softer face might be used for tasks that require a gentler touch, such as working with delicate materials or performing finishing work. When the hammer strikes an object, the force of the impact creates stress waves that propagate through both the hammer and the target material. These stress waves can cause different types of deformation depending on the material properties of the target. For metals, the stress can cause plastic deformation, where the material changes shape without fracturing. For brittle materials like concrete or ceramics, the stress may exceed the material's fracture strength, leading to cracking or shattering. Engineers must understand these material behaviors to design hammers that are suited for specific tasks, ensuring that the tool's force is applied in the most effective and controlled manner. The dynamics of the impact also include considerations of damping and vibration. When a hammer strikes a surface, not all the kinetic energy is transferred to the target. Some of it is converted into vibrational energy. These vibrations can travel through the hammer and into the user's hand and arm, causing discomfort and fatigue over time. Modern hammer designs often incorporate damping materials and technologies to mitigate these vibrations. For instance, handles made from composite materials or featuring rubber grips can absorb some of the vibrational energy, reducing the amount transmitted to the user. This not only enhances user comfort but also improves the precision and control with which a hammer can be used. Moreover, the angle at which the hammer strikes the target also affects the efficiency and outcome of the impact. An optimal angle ensures that the maximum amount of kinetic energy is transferred directly into the target, minimizing energy loss through deflection or glancing blows. Skilled users intuitively adjust their hammering technique to achieve this optimal angle, but engineers can also design hammerheads with specific shapes and weight distributions to aid in achieving more effective strikes. The physics and engineering behind hammering are intricate and multifaceted, involving a deep understanding of mechanics, material science, and ergonomics. From the biomechanics of the user's swing to the material properties of both the hammer and the target, each aspect contributes to the tool's effectiveness and efficiency. Modern advancements in materials and design continue to refine hammers, making them more powerful, comfortable, and precise. ensuring that this ancient tool remains an essential part of our toolkit in various applications. The moment of impact between a hammer and an object is a prime example of applied physics and engineering principles in action. When the hammer strikes an object, kinetic energy generated by the user's swing is transferred to the hammerhead. This kinetic energy is then transformed into mechanical work upon impact. The force exerted by the hammer is distributed over the contact area of the hammer face. This distribution is crucial because it influences the stress concentration within the material being struck. If the stress exceeds the material's yield strength, plastic deformation occurs, meaning the material will permanently deform. If the stress surpasses the material's fracture strength, the material will crack or shatter. The hammer's face shape, whether flat, rounded, or chiseled, determines how the force is distributed across the material's surface. A flat face tends to spread the force over a larger area, reducing the likelihood of material fracture, while a chiseled face can concentrate force into a smaller area, increasing the potential for cutting or breaking the material. The hardness of the hammer face plays a significant role in the efficiency and effectiveness of the impact. A harder hammer face can better resist deformation and wear, ensuring consistent performance over repeated use. However, if the hammer face is too hard, it may become brittle and prone to chipping or breaking, especially when used on hard materials. Conversely, a softer hammer face can absorb more impact energy, reducing the risk of damage to both the hammer and the material being struck, but it may deform more easily under heavy use. Engineering the optimal balance of hardness and toughness in the hammer face material is a critical aspect of hammer design, often achieved through specialized heat treatment processes such as tempering and quenching. The dynamics of the impact are further influenced by the velocity and angle at which the hammer strikes the object. A higher velocity impact results in greater kinetic energy and, consequently, a more forceful blow. The angle of impact can also affect the distribution of force and the resulting stress patterns within the material. A perpendicular strike maximizes the transfer of kinetic energy into the object, while an angled strike can introduce shear forces that may cause the material to slide or fracture along specific planes. Understanding these dynamics allows engineers to design hammers that are tailored to specific tasks, optimizing their performance for driving nails, shaping metal, or breaking concrete. Vibration and shock waves generated during the impact are additional factors that must be managed through engineering design. When the hammer strikes an object, a portion of the kinetic energy is converted into vibrational energy, which propagates through the hammer and into the user's hand. Excessive vibration can lead to user fatigue and discomfort, potentially reducing productivity and increasing the risk of injury. To mitigate these effects, modern hammers often incorporate vibration damping features such as cushioned grips, shock-absorbing materials in the handle, or specially designed internal damping systems. These features help to absorb and dissipate vibrational energy, improving user comfort and extending the usability of the hammer. The interplay between the hammer's mass, velocity, and the mechanical properties of both the hammer and the object being struck is a complex system governed by the principles of mechanics and material science. The mass of the hammer head affects its momentum, with heavier heads delivering more forceful blows at the same velocity. However, increased mass also requires more effort from the user to wield effectively, highlighting the need for ergonomic design considerations. By optimizing the balance between head mass, handle length, and material properties, engineers can create hammers that maximize efficiency and effectiveness for specific applications while minimizing user strain. In addition to the physical aspects of hammer design, the manufacturing process itself is an area of significant engineering expertise. The precision forging of the hammerhead, the selection and treatment of materials, and the assembly of the handle all require careful consideration and the quality control. Advanced manufacturing techniques, such as computer numerical control, CNC, machining and automated heat treatment, ensure that each hammer meets stringent performance and durability standards. These techniques also enable the production of specialized hammers with unique features, such as magnetic nail holders, integrated pry bars, or interchangeable heads, further enhancing their functionality and versatility. The engineering and physics behind the moment of impact in hammering involve a complex interplay of forces, material properties, and design considerations. By understanding and optimizing these factors, engineers can create hammers that deliver precise, powerful blows while minimizing user fatigue and maximizing durability. This intricate balance of science and design is what makes the hammer not just a simple tool, but a finely tuned instrument of mechanical efficiency. When striking an object with a hammer, the energy from the impact is not only transmitted to the object being hit but also reverberates through the hammer itself, generating vibrations. These vibrations travel through the handle and into the user's hand and arm, causing discomfort and fatigue over extended periods of use. This phenomenon is particularly pronounced in repetitive tasks, where continuous exposure to vibrations can lead to conditions such as hand-arm vibration syndrome, HAVS. To mitigate these effects, modern hammers incorporate damping technologies that aim to absorb and dissipate the vibrational energy, thereby enhancing user comfort and reducing the risk of injury. The engineering behind damping technologies in hammers involves a careful selection of materials and structural design. Rubber and polymer inserts are commonly used within the handle to absorb the vibrational energy. These materials have viscoelastic properties, meaning they exhibit both viscous and elastic characteristics when deformed. When the hammer strikes an object, the viscoelastic materials deform, converting some of the kinetic energy from the vibration into thermal energy through internal friction. This energy transformation reduces the amplitude of the vibrations transmitted to the user. The effectiveness of this damping can be fine-tuned by varying the composition and thickness of the inserts, allowing manufacturers to design hammers for specific applications and user preferences. Furthermore, the design of the hammer handle itself plays a crucial role in vibration reduction. Handles with ergonomic contours not only improve grip but also help to distribute the forces more evenly across the user's hand, reducing localized stress points that contribute to discomfort. Some advanced designs incorporate segmented handles, where the handle is divided into sections connected by flexible joints. These joints act as additional dampers, allowing slight movement between the segments to further dissipate vibrational energy. This segmented design can significantly enhance the overall damping effect without compromising the hammer's structural integrity or the user's control over the tool. In addition to material selection and handle design, the attachment method of the hammer head to the handle also influences vibration transmission. Traditional hammers often use a single-piece construction or a rigid attachment, which can result in higher vibration levels. Modern hammers, however, may employ shock-absorbing connections, such as cushioned mounts or spring-based systems, to decouple the hammer head from the handle to some extent. These connections allow for slight relative movement between the head and the handle, providing an additional layer of vibration isolation. This principle is similar to how shock absorbers work in vehicles, where the suspension system isolates the passenger compartment from road vibrations, ensuring a smoother ride. The physics behind these damping mechanisms can be analyzed using principles from dynamics and wave propagation. When a hammer strikes an object, the impact generates mechanical waves that travel through the hammer's structure. These waves are characterized by their frequency, wavelength, and amplitude. By incorporating materials and design features that alter the propagation characteristics of these waves, engineers can reduce the energy transmitted to the user's hand. For example, viscoelastic materials introduce damping forces that are out of phase with the vibrational motion, effectively cancelling out some of the energy. The segmented handle design introduces additional points of reflection and refraction for the waves, further dispersing their energy and reducing the overall vibrational amplitude. Moreover, Advanced computational tools and simulation techniques are employed to optimize hammer designs. Finite element analysis, FEA, allows engineers to model the behavior of different materials and structures under vibrational loads, predicting how design changes will affect performance. By simulating the hammer's response to impact, engineers can identify areas of high stress and vibration, enabling targeted improvements. These simulations can also account for the complex interactions between different components, ensuring that the final design achieves the desired balance between strength, durability, and vibration damping. The engineering and physics behind vibration damping in hammers are multifaceted, involving a blend of material science, structural design, and dynamic analysis. By leveraging these principles, modern hammers are able to provide greater comfort and safety for users, allowing them to perform their tasks more efficiently and with less risk of injury. The continuous advancement in this field reflects the broader trend in tool design towards enhancing user experience through innovative engineering solutions. The humble hammer, thus, continues to evolve, embodying the ingenuity and precision of contemporary engineering practices. There are many types of hammers, each engineered for specific tasks, reflecting a deep understanding of engineering and physics principles. The claw hammer, for instance, is a versatile tool primarily used in carpentry. Its distinctive feature is the curved, forked end, known as the claw, designed for extracting nails. This function relies on the principles of levers and mechanical advantage. When a nail is wedged into wood, the claw hammer allows the user to apply a relatively small force to the handle, which is then magnified at the claw to extract the nail. The curvature of the claw provides the necessary geometry to maximize this mechanical advantage, allowing for efficient nail removal with minimal effort. The balance between the hammer's head and handle length is critical. A well-designed claw hammer must be light enough for precise control yet heavy enough to generate sufficient force for driving nails. In metalworking, the ball peen hammer stands out with its rounded peen opposite the flat striking face. This design is optimal for tasks such as shaping metal, peening rivets, and rounding edges. The physics behind the ball peen hammer involves impact dynamics and material deformation. When the rounded peen strikes metal, it concentrates force over a smaller area compared to a flat face, allowing for more precise shaping and deformation of the material. This capability is essential in tasks where controlled force application is necessary to avoid overworking or damaging the metal. The hardness of the hammerhead, typically made of high-carbon steel, is crucial in ensuring that it withstands repeated impacts without deforming, thus maintaining the tool's effectiveness over time. Sledgehammers, characterized by their heavy heads and long handles, are engineered for tasks requiring brute force, such as demolition and breaking concrete. The physics of a sledgehammer involves both momentum and energy transfer. The long handle allows the user to generate significant angular momentum during the swing, which, combined with the mass of the head, results in a powerful impact force. This force is essential for breaking through tough materials like concrete and masonry. The handle length also provides leverage, enabling the user to apply force more efficiently and with greater control over the direction and intensity of the blow. The durability of the sledgehammer is another engineering consideration. The head must be made of tough, hardened steel to withstand repeated high-impact blows without fracturing or chipping, while the handle must be designed to absorb shock and reduce user fatigue. Rubber mallets are another specialized type of hammer, used in applications where softer impacts are required to avoid damaging the workpiece. These hammers feature heads made of rubber or other resilient materials, which absorb much of the impact energy and distribute the force more gently. The engineering behind rubber mallets involves understanding the material properties of the head, ensuring that it is soft enough to prevent damage but still firm enough to effectively transmit force. The handle design also plays a role in ensuring comfortable use, often incorporating ergonomic grips and shock-absorbing materials to minimize user fatigue during extended use. In automotive and industrial settings, The dead blow hammer is a sophisticated tool designed to deliver controlled force without rebound. The head of a dead blow hammer is filled with sand or lead shot, which moves within the head to absorb the energy of the impact. This design minimizes the rebound effect, allowing for more precise control of the force applied to the workpiece. The physics behind the dead blow hammer involves the principles of momentum transfer and energy dissipation. When the hammer strikes, the moving mass inside the head helps to absorb and dissipate the kinetic energy, reducing the chance of the hammer bouncing back and providing a more controlled, effective blow. This feature is particularly useful in tasks that require precise application of force without damaging delicate components. The diversity of hammer designs is a testament to the intricate application of engineering and physics principles tailored to specific tasks. Each type of hammer, from the versatile claw hammer to the powerful sledgehammer, embodies a unique combination of material science, mechanics, and ergonomic considerations. These tools have evolved over centuries, continuously refined to enhance their functionality, efficiency, and user comfort. Understanding the engineering and physics behind each type of hammer not only highlights their complexity but also deepens our appreciation for these seemingly simple yet profoundly effective tools that have shaped human civilization. In conclusion, the humble hammer is a marvel of engineering and physics. Its design is a culmination of centuries of technological advancement, material science, and ergonomic considerations. From the basic principles of levers and momentum to the sophisticated damping technologies in modern hammers, every aspect of this tool is crafted to maximize efficiency, durability, and user comfort. The next time you pick up a hammer, remember that you are holding a piece of engineering history, a tool that has been refined over thousands of years to serve humanity in countless ways. The lever principle is fundamental to the hammer's operation. The handle acts as a lever arm, magnifying the force exerted by the user's hand. This leverage allows even modestly strong individuals to generate significant impact forces. The length and shape of the handle are meticulously designed to optimize this leverage. Longer handles provide greater force but require more space to swing, making them suitable for demolition or driving large stakes. Shorter handles offer more precision and control, ideal for tasks like carpentry or delicate metalwork. The handle's cross-sectional shape, often oval or rectangular, prevents it from rotating in the hand during a swing, ensuring consistent delivery of force. The physics of impact and energy transfer in a hammer are also intriguing. When swung, the hammerhead accumulates kinetic energy proportional to its mass and the square of its velocity. Upon striking an object, this kinetic energy is transferred to the target. The efficiency of this transfer is influenced by the hardness and shape of the hammer face. A hardened steel face minimizes energy loss through deformation, while a textured or slightly convex surface can prevent slippage, concentrating the force on a smaller area and increasing the stress on the target material. This is particularly important in tasks requiring high precision, such as driving nails or chiseling. Material science plays a critical role in the development of both the hammerhead and handle. The head must be hard enough to resist wear and deformation, yet tough enough to absorb shocks without fracturing. This balance is often achieved through heat treatment processes like quenching and tempering, which enhance the steel's microstructure. Advances in metallurgy have led to the development of specialized alloys that offer superior performance. For example, high-carbon steel provides excellent hardness, while alloying elements like chromium and molybdenum can improve toughness and resistance to corrosion. Ergonomic considerations are paramount in modern hammer design, addressing the need for user comfort and injury prevention. The handle's design incorporates features to reduce strain on the user's hand and arm. Contoured grips, often made from rubber or polymer composites, fit naturally in the hand, reducing the effort required to maintain a firm hold. Anti-vibration technologies, such as internal damping systems or cushioned grips, mitigate the transmission of shocks and vibrations from the hammerhead to the handle. These innovations are essential for professional users who may swing a hammer thousands of times in a single day, helping to prevent conditions like carpal tunnel syndrome and tendinitis. The dynamic interaction between the hammer and the target material during impact is a fascinating study in physics. The force of the blow generates stress waves that propagate through the material, causing deformation or fracture depending on the material's properties. In ductile materials like metals, the stress may cause plastic deformation, bending or shaping the material. In brittle materials like stone or concrete, the stress can exceed the material's tensile strength, causing it to fracture and break. Engineers must understand these interactions to design hammers that perform optimally for specific applications, whether shaping hot metal on an anvil or breaking concrete slabs in construction. Furthermore, the evolution of hammer design reflects broader trends in technology and society. The introduction of new materials and manufacturing techniques has continually pushed the boundaries of what hammers can achieve. The development of composite materials, for instance, has led to lighter, stronger handles that reduce user fatigue. Computer-aided design, CAD, and finite element analysis, FEA, allow engineers to simulate and optimize hammer performance before production, ensuring that each new design iteration represents an improvement over its predecessors. In summary, the humble hammer embodies a perfect blend of engineering and physics principles, honed over centuries of innovation. Its seemingly simple design belies a complex interplay of forces, materials, and ergonomic considerations. As we continue to advance technologically, the hammer evolves alongside us, integrating new materials and design philosophies while retaining its fundamental purpose. Whether used for construction, metalworking, or demolition, the hammer remains an essential tool, a testament to human ingenuity and our ability to harness the principles of engineering and physics to meet our needs. The next time you pick up a hammer, take a moment to appreciate the sophisticated engineering that makes this timeless tool so effective. Thank you.